Hi, welcome to our talk, x86-less ScyllaDB, exploring an all-ARM cluster. My name is Mike Bennett, and I'm a solution architect here at Ampere Computing. I've been working in IT for the past 18 years, so I've seen a lot of different database technologies. And for the past 9 years, I've been working in solution development for OEMs, where I've helped make ways to run those kind of applications faster. For that reason, I enjoy servers with many cores because they help things run faster. And I recently moved to California from Texas, being a reverse migrator against the trend.
Hi, I'm Keith. I'm responsible for apps engineering at ScaleFlux. I've been in the memory and storage business for close to 20 years now. I really enjoy it. I was born in Mountain View, so just a little bit before Google. So I've enjoyed kind of growing up in Silicon Valley. So our agenda today, we're going to talk a bit about the cluster that we built using 100% ARM cores, and no x86 was harmed in the building of this cluster. We're going to introduce Ampere and ScaleFlux, our two companies. Then we're going to look at the benchmarking setup and talk about some of the results we achieved, which I think are quite impressive. And then lastly, we'll wrap up with some ways to get in contact with us in case you want to learn more.
Going into our cluster configuration, you can see here our all ARM powered cluster. Not a single x86 processor was needed. To build this cluster, we started with 3 servers. Those are our Mount Collins platform from Foxconn. Each of these systems has a Ultramax M2830 processor, which is our way of saying it's 128 cores running at 3 gigahertz. We had 256 gigs of RAM per node, but if you went to a dual socket configuration, you could have up to a terabyte of memory. Inside of each of these servers, we had 4 ScaleFlux SSDs, which have their own Cortex cores inside of them as ARM processors. And we used 3 client machines running Ampere Ultra Q8030, which is an 80-core version of our 3 gigahertz processor, pushing the different test configurations that we'll go over later to our ScyllaDB instance. For the operating system inside of the cluster, we went with SUSE Enterprise 15.4 because they contributed some to helping us get the hardware resources that we needed for this testing. And we also used 100 gigabit Ethernet networking powered by Mellanox ConnectX 6 NICs. So in this entire cluster, we didn't need a single x86 instruction to help us out. So the reason that we think it's important to do this test and to demonstrate an all ARM-powered ScyllaDB cluster is because we think that it will provide a lower power solution than equivalent clusters available today, and that you'll see a higher CPU density per rack and even per node with up to 256 cores, available in Ampere systems, and that all of this is going to come together to give you a more highly performant ScyllaDB instance and cluster. So before we go into the results, we'll give you a little bit of an introduction on our two companies. First, we have Ampere, who I work for. We developed the world's first cloud-native processor, the Ampere Ultra, which is available in up to 80 cores at 3 gigahertz and has 8 memory controllers for DDR4 up to 3200. And then we followed that on with our Ultramax line of CPUs, which are the same Neoverse N1 core as the Ampere Ultra, but you can get up to 128 cores per socket and at 3 gigahertz, and again with 8 memory controllers. Some of the things that differentiate our processors from the competition is that we are single-threaded. So one core is one thread, and that helps us have the ability to run all of our cores at max frequency. So there will be less frequency scaling up and down based off of TDP and other factors as some systems do. With Ampere servers, you can run all cores at 3 gigahertz, without hitting your TDP. And we have large, low latency private L1, L2 caches, as opposed to legacy architectures that use a large L3 cache to share information among the cores. And yeah, with our maximum core count, you can get up to 256 cores in a 1U server, and that's using the UltraMax M12830.
Yeah, so at ScaleFlux, we like to make what we call a better SSD. So we take a data center class, NVMe SSD, in common form factors such as U.2 or U1.S at 4 terabyte to 16 terabyte physical capacity points. And we marry those with compute engines for acceleration. Sometimes this is called computational storage. So some of those compute capabilities can be transparent compression, decompression, data filtering, or security acceleration. So you combine the performance and all the goodness of a really fast NVMe SSD with these rocket engines that can really boost performance in certain applications. So let's see what the benchmarking results look like. I think this is the kind of the highlight of the show here. So first things first, we have to load a database. I want to highlight some of the choices that we made in loading data. First, we chose a replication factor of 3. We didn't have to specify a compaction strategy because by default, we're going to get incremental compaction with Scylla Enterprise. We're using the shardware driver from the Cassandra Stress utility provided by Scylla. And we're going to use a variable column size. We're not going to just do a fixed column size here. And we also updated a little bit after the sequential population of the drive, so a little bit of overfill. So the first scenario that we're going to look at is 100% read with the Gaussian distribution. So this is going to touch memory, it's going to touch a little bit of disk, and we chose to look at 100% read because we wanted to see what kind of latency, read latency we can get out of the cluster without the writes getting in the way. In the second scenario, we want to look at a more of a realistic, real-life kind of workload. We do 75% read and 25% write. And again, we're going to use a Gaussian distribution, so we're touching memory, we're touching a little bit of disk. And in the last scenario, we did something really interesting. We did 50-50 read-write, but we're going to use a really small data set, so we just fit in memory and see if we can find any bottlenecks in our cluster. So first, looking at read, I think the first thing to highlight here is that we achieved 1.4 million operations per second. And then the second thing to look at is we did that at P99 latencies of less than a millisecond. So this is a very, very, very high performance cluster when it comes to read. The last thing to note here is that the CPU utilization is quite low because the read operation wasn't as CPU intensive as we'll see in when we add writes. So in our 75-25 quote-unquote real-world test scenario here, everything's the same as the read, except for adding in those writes. We're still using a Gaussian distribution. We're still looking at the whole data set with that distribution. But now we see a couple things. We see that we're down, we're still at over a million IOPS. We're at 1.1 million. Part of the reason for that is we have that write activity that's happening, and we have other things to manage with the database. We are doing about 100 running compactions during this benchmark on average we saw. And of course, with that write to read interference and all that activity going on, the read latencies did go up a little bit, but still fairly respectable. And we could have backed off on the performance a little bit if we wanted to. So remember, in these tests, we're just really trying to put the pedal to the metal here and push as much as we can out. And if we wanted to try to back off on the aggressiveness of the operation per second, we would see those latencies kind of fall proportionally with that. And the last slide we'll look at is the 50-50 case. And here we kept the data set in memory and really tried to torture the system. And here we did hit over 80% CPU load, but we got to 1.4 million operations per second again. And in this case, we don't see so many compactions because our data size we're writing is so small, right? So basically, this consists of memtable flushing as the sole write activity going on in the disk. We do see that slightly improved the read latency here, but results very similar actually to the 75-25 case, which I think is quite interesting.
Thanks, Keith, for going over those results. Earlier, after we did the cluster setup, we gave some of the reasons why we were doing this experiment. And so now, looking back at those, we can see that we did have a low power utilization, especially relative to the performance that we got with 1.4 and 1.1 million operations per second, depending on the test. And that was using under 4 watts per CPU. Total system power draw was between 410 and 490 watts, including storage, network, memory. And so when you think about your existing rack footprint and how many more of the next generation processors you might be able to get, it's common to see other systems coming out that advertise power draws of 8 to 10 watts per core. And they're different cores than our cores, and so performance is going to be somewhat, is not going to be exactly the same. But we draw half or less of the power that comparable CPU cores that your ScyllaDB instance might be running on now use. And we do it with a higher CPU density, which means you need fewer servers in order to achieve this performance, and you lower your costs and your man hours that you have to spend troubleshooting servers that have issues, because we put 128 cores in each socket, and we can have up to 2 sockets per system. So you can have 256 cores per server and easily over 10,000 cores per rack if you use one-use servers. And so all this, is going to give you a really highly performant system, and it's going to do it in a smaller footprint than you're going to see with comparable x86 systems. So if you want to give running ScyllaDB on ARM a shot, you can use our Ampere developer access program to get access to some hardware. You can either use bare metal servers that we host in our lab or send to you. And then alternatively, we can give you access to a cloud environment hosted on Azure, OCI, or one of the other many public clouds, and you can run your workload there. My team also has a bunch of solution architects like myself available, and so we'll provide resources to help you get up and running and overcome any problems that you face along the way.
Thanks, Mike. Yeah, and here at ScaleFlux, we also have a POC program. You can request samples at the email address here, info@scaleflux.com. Be sure to mention you saw us at the ScyllaDB Summit. You can learn more about our company or our website, scaleflux.com. And then lastly, feel free to reach out to me if you have any questions or just want to talk storage. I do love talking about storage, so be warned. Thank you.
And thanks for coming to our talk. If you want to stay in touch, you can see all of our information below.